welcome back to my YouTube channel. Today we are going to solve a medium question on lead code, which is count good numbers. Let me read the problem statement. A digit string is good if the digits 0 indexed at even indices are even and the digits at odd indices are prime. Okay, for example 2582 is a good because the digits are at even positions are 0 1, which are 2 and 8, and at even positions and are even, and the digits 5 2 are at odd positions and are prime. However 3245 is not a good because 3 is not an even number. Given an integer n, return the total number of good digits strings of length n. Since the answer may be large, return modulo division of 10 power 9 plus 7, which is a prime number. A digit string contains 0 through 9, that may contain leading zeros as well. We can have a leading zeros. So we will be given n, which represent n positions, let's say, and for every occurrence of odd position, we can have primes 2 3 5 7. We cannot have 11 because it's not a digit. For even position, we can have even numbers. The even numbers, single digit even numbers are 0 2 4 6 8. There were 5 digits of even numbers and 4 prime digit numbers, single digit numbers. These are the possible positions. So for even position we have 5 choices, and for every the second position we can have 5 choices, and for every odd position we have 4 choices. So we can say 5 times 4 times 5 times 5 times 4, something like that, and so on. So for a given n, we will be having n divided by 2 plus n divided by 2. Since this is a zero based index, we will be doing n plus 1 by 2, and this is for odd. So these many times we will have to calculate multiply 5, and these many times we have to multiply 4. So for given, let's say for this position 4, let's take this example. 4, we have 2, this should be multiplied because there are 2 even positions and 2 odd positions. So it's something like 5 times. For even we have 5 choices, and we will multiply this. For odd we have 4 choices, so which is nothing but 25 times 16 is 400. This is the answer. But yeah, that is the solution for it. But we have to think of an optimization, because here n is 10 power 15. If we keep doing multiplying 5, let's say 10 power 5 15 times, it will time out. We have to think of a better solution. So here what we are doing is, the answer is something like 5 power n plus 1 by 2, excuse me, and 4 power n divided by 2. This is the answer. So let's say if you want to calculate x power n, how will we do it optimally? Like it is something like multiply x n times x time x time x time till n x, right? So what we can do is we can do binary exponentiation, which is something like we want to calculate x power n, right? What we can do is we will first calculate what is x power n by 2. If I know what is n by 2 x power, let's say if we can write it like this, right? X power we can write this as like, right? So here if you see, we are doing the same work twice here. So if we calculate this one, and we can make use of this value and we don't need to calculate this again. And similarly, let's say if x power n by 2 can be again written as x power n by 4 times x power n by 4, right? So if we know this one, we can discard this part and we can directly use this value. So the process of doing this thing is called binary exponentiation, and I'll try to implement it so that you can see how we can do it. So the answer is, let's say the return type is int, so let's say we will write a power function n plus 1 divided by 2. This is for 5, and for odd position we have n divided by 2, and we will have to do a modulo division on the whole part. We will return a log now x power n. Okay, and we will define a modulus value. In Java we can represent numbers like this for readability, which is syntactically correct, or we can do something like 1a 9 plus 7, which is also fine here. So this is the one. Now let's try to implement this one. What we can do is, if n is equals to 0, we can return 1, right? Like anything power 0 is 1, right? So x power 0 is 1, right? Now let's calculate where of this should be end. Okay, value, what we can do is power of x times n by 2. If n mod 2 is equals to 1, we will divide it by x mod. Got it. So if we are dividing n by 2, but there is, let's say there is one odd power, let's say 5, so we can divide 2 2, but one extra one thing is there, right? So we will multiplying that x. So since we calculated the value, we can do these two calls by doing return value times value whole mod. Yeah, this is it. Let me try to run this. uh, you should be here. Okay. uh, if it is hard, we are doing this one. I think this should be on top. If it is odd, we will do one extra thing. And let me try to run now. Yeah. So before I submit, I'll try to do time and space complexity analysis. So here we are not using any space, and let's say this space, the space will have the stack space. This will go till log of n, because this n is keep dividing by off every time. So space will be log of n of base 2, and we go off, and the time is, well, time is also log of n, because we are going till log of n height, and we are doing some constant operation, but we are doing twice, which is 2 times log of n, which is log n. So let me try to submit this. Accepted. So we can avoid this space complexity by converting this recursion into a while loop. Please let me know in the comment section if you are able to do that, instead of like implement this in while loop instead of a recursive call. So that's it for this video. Thank you for watching. Please like, share and subscribe to my YouTube channel. See you in the next video.